Hello everyone. In the previous lecture, we learned we learned the notion of groups, uh, and our discussion was largely motivated by some naive discussion of the notion of symmetry. So let me mention once again that the previous discussion was only naive in nature, and one of the aim or anyway that we will do along this course is to be able to uh, discuss all these notions in a formal manner, in a precise manner. Okay, and the precise thing that we learned in the previous lecture is the notion of groups. Okay, so it comes with this bunch of 5 conditions, etc. So that you must have seen. Okay, uh, yeah, so you have also had some concrete examples in the sense that it was left for you to show that these examples they do provide us they are examples of groups. This G, which consists of solutions of z square equal to 1, solutions of this equation in C, combine with respect to multiplication. Okay, and here if you consider the set of solutions of this equation z power n equal to 1 inside C, and then this set forms a group with respect to multiplication of complex numbers. Okay, so this is called the group of nth roots of unity that you know, and this is customary to use the symbol mu sub n to denote this group. Okay. Okay, and next we made this notion of finite and infinite groups. So we call a group finite or infinite depending on the cardinality of its underlying set G. Okay. Yeah, and also probably this is something that I did not mention. I think I will mention in some of the upcoming lectures that if you have a group G comma star, by abuse of notation, we will just say that we have a group G. Okay, so by abuse of notation. So unless we specify this symbol star, it doesn't make any sense. Okay, but usually it will happen that the star would be clear from the context. Okay, so in that case, we will just write the symbol G in order to denote the group G comma star. Okay. Okay, great. Anyway, so here you see that something I have written down. Anyway, so this you get to see because I already recorded this lecture, but there was no audio for some reason. So during that time, I wrote this stuff. Okay, so we are going to have certain examples. So we are going to begin with S1. So S1 consists of all the tuples xy inside R2 such that sum of the squares of their coordinates is equal to 1. Okay. You're going to ask me why do I use this letter S here? Okay, I don't know, but I think the reason is that S here stands for sphere, and this notation makes sense because here if you add one more coordinate, in other words, if you look at all x, y, z inside R3 such that x square plus y square plus z square is equal to 1, then what you get is the sphere, right? Or is the unit sphere with center at the origin. Okay, and then the letter S does make sense. Okay, and this is called S1 because this is circle. So locally, if you just look at small segments, they look like line. In some sense, there is one-dimensional nature. Anyway, I'm just trying to justify the notion. So what I was saying doesn't have anything to do with the kind of things that we are going to see from now on. So you have so you have this unit circle with center at the origin. On that you can define a map star from S1 cross S1 to S1. Okay, which given 2 points x1 y1 and x2 y2 from S1, x1 y1 star x2 y2 is defined to be this point. Okay. Yeah, here is something. So first of all, you can ask me from where did I get this formula. Okay, I'll not tell you right now, but I think this is something with some amount of work. I think you will be able to see that you have already seen this expression in some form or the other somewhere. Okay. Anyway, so yeah. So here, there is something that you need to do. So for example, if you look at the map from R to R, which sends x to 1 over x, okay, you can consider some such map naively at least. Okay, and then the immediate question that comes in the mind is whether this map makes sense or not. Okay, we can talk about a map, but then the point is that, or we can have hope of considering a map, but in that case we should first ask whether this makes any sense or not. Okay. So as you will observe in a moment that this doesn't make any sense, because at the point x equal to 0 there is trouble, because 1 over 0 doesn't make any sense. In other words, inside R there is no element such that it products with 0 gives you 1. Okay. Anyway, so whenever you consider a map, or whenever we have, we would like to consider a map defined by some sort of expression or a formula, or it is just defined. The first question is whether the definition itself make any sense or not. Okay, so the reason behind discussing about this example x going to 1 over x is that in this context also we need to ask whether this x1 x2 minus y1 y2 and so on, whether this is an element of S1 or not. Okay, so the first question is that whether this map is actually a true map or not. Okay, until we verify that this map makes sense, it doesn't make kind of much, there is not much point in discussing whether this forms a group or not. It's the first task. Okay, you can also say that just because I am asking you to consider the map, or at least this question asks us to consider this map, so this question will be meaningful only when this point lies inside S1. That is true, but okay, anyway. So that's just a formulation of this question or this exercise. But to make sure that you understand, to make sure that we understand what's going on here, we need to make sure that this is indeed an element of S1. Okay. So first we need to make sure that the image of this map is contained inside the set on the right hand side. So we usually say that this map is well defined. This is not the standard way of saying, because whenever we talk about image of some map, we are under the hypothesis that the map itself is a map, it's a true map without any trouble. In other words, this is a well defined map. And the next task is to see whether S1 forms a group under this map star or not. Okay. Okay, so you pick 2 points x1 y1 x2 y2 from S1, and then we try to see whether this lies inside S1 or not. Okay, so to show that sum of the squares of the coordinates is equal to 1, so by an elementary algebra and certain cancellation laws, it follows that the sum of the squares give you 1. Okay, so it follows that so this map is well defined. The map star that we have just introduced, we just got to introduce in this exercise. So this map is well defined. Fine. So you are done with part 1. So now we focus on part 2, right? We have to determine whether S1 forms a group on the star or not. So recall that there were 5 conditions to work with. So you have this first condition, second one, and the first condition is anyway met, that S1 is a set. We do have a composition law star. In other words, star has to be a map from G cross G to G. Okay. So for any GH inside G, its image under this map should be an element of G. In other words, so we need to verify that, and that we have done. We have shown that this is indeed an element of S1. Okay, so we are done with the first 2 conditions. The third condition is that is the associativity. I hope I mentioned that property is called associativity. Yeah, okay, so this is called associativity. I did mention. Just give me a moment. Yeah, so we need to show that you pick 3 points x1 y1 x2 y2 x3 y3. So first you compose the second and third point, and then compose x1 y1 with this one. That's same as first composing the first 2 points and then composing the outcome with x3 y3. Okay, so I leave it to you to verify that this does have this associativity property. Okay, this is not too difficult, but this might be some sort of how to say some maybe bit maybe little extensive use of algebra, all the elementary, so you need to do it. Okay, and the next property is the fourth condition, where you have to look for some element E such that xy star E is same as E star xy, and all of them should be same as xy. Okay, and this is not too difficult to observe that we do have one such element, namely 1, 0. If you look at x, y star 1, 0, you get xy, and then similarly 1, 0 star xy, that also gives you xy, and it happens for every xy inside S1. Okay, so you are done. Okay, yeah, and now we are going to focus on the fifth condition. Before we get into the fifth condition, here you can ask something, that from where did I get this point 1, 0? Okay, so let me not tell you right now. Okay, I'll just tell you after discussing this proof, discussing the remainder of the solution. So we need to show that for every g there is some x, there is some y, such that x star g is g star y. I hope I wrote it in that order. So that x star g is g star y, and that is equal to the identity, right? X star g is g star y, that is equal to identity. So we need to come up with this 2 points such that the given point composite with this one gives you the identity back, and this point combined with the given point gives you the identity back. That is something one can also try to see. So this is an elementary computation that one can see. So this will happen under, if you take x1 y1 and x2 y2 be x comma minus y, okay, you can verify this computation. Yeah, and then that proves that S1 along with the composition law that was given to us, so that forms a group. Okay, so here there are certain questions that you may ask. So while discussing, while doing math, the terminology is there really important. The terminology is the use of verbs, articles, and in other words, so how each sentence is formulated. That is really important. So here we say that there is an element T called the identity element. Okay, so this article is really a crucial article. So here, instead of calling it an identity element, we say that E is called the identity element. So this may suggest you that there cannot be more than one identity elements in a group. Yeah, that is true. We will also have it in the form of an exercise sometime soon. That in a group there is only one identity element. Okay, there is at least one identity element that is guaranteed by what we have. Okay, and one can show that there cannot be more than one. Okay, yeah. Yeah, okay, great. So the point is that okay, so here I came up with this point 1 comma 0 and it worked, right? So but from where did I get it? Okay, so let's go back to some of the remarks in the footnote. So the point is that we need to there are several ways of doing it. Okay, so first of all, if you are able to guess it immediately, then you are done. If not, so then this could be one of the approaches, okay, that may save us. So first you assume that there is some identity element. In other words, we assume that S1 contains an element A comma B. Note that this is part of the rough work. Okay, so this is something we do. We kind of do go through, but this is not something that you write in a proof. Okay, so you write out the final output essentially. Okay, but this is important for explaining. Okay, this is not important. Within the proof. Why? You may say that okay, you are able to come up with the proof just because you did the rough work. You are right, but this is a standard practice. So while kind of writing precise proofs, we usually hide, we usually do not tell how did we arrive at the solution. Okay, I'm not saying that this is customary to hide that information. This is not customary. So while discussing or while lecturing or while explaining, it is expected that we'll tell the secrets. Okay, or kind of how did you came up with the solution, so that the audience finds it somewhat natural. But while writing down solution, we just do not kind of share all the rough work that we had done. Okay, otherwise the audience it will be very much troublesome for the audience. Anyway, so let's assume that we have an element A comma B inside x1. That works. In other words, it works as identity element. In other words, A comma B star xy is same as xy star AB, and that is same as x comma y, and it holds for any xy inside S1. Okay, so now we so we needed to figure out whether there is such an element or not, and to be able to figure out, you first assume that there is one such. Okay, we assume that there is one such element A comma B. You can also ask me, so why you are making this assumption? It may happen that there is no such element. Okay, but you do not know whether there is such an element or not. The idea is that we'll assume that such an element exists. Okay, that is an element AB exists such that these equalities holds for any xy inside x1, and from this information we will deduce certain condition that will we will deduce certain necessary conditions for AB to satisfy. Okay, and from there we will have certain choices left for AB, and that will essentially do, right? Okay, but no, that will not do, because if you assume that there is one such element, that works. Okay, and if you are able to obtain certain necessary conditions for A and B, even then it does not say that you have found such an element. It only says that if there is one such element, then that a comma b has to satisfy those properties. It does not guarantee that there is such an element. Let me repeat. If we assume that there is one such element and then we are able to deduce some necessary conditions for a and b, it does not guarantee that there is one such element, a comma b, okay, satisfying this condition. If we deduce the necessary condition, because we have deduced this necessary condition only under the hypothesis that there is one, okay. So if there is one, then certain necessary conditions has to hold, okay, and in that case we know, if there is any such a b, what it has to be, and then we have to see whether that a comma b satisfy this condition or not, okay. Anyway, so yeah, so we assume that there is one such element a b such that this holds, and in particular, sorry, just give me a moment. How this got turned on? Yeah, so this equality has to hold, and this holds for any xy inside S1. Okay, now you can substitute any of your favorite xy to see what happens. So you can substitute 0, 1 for instance, and that will tell you that a is 0 and b is 1. Okay, great. That will tell you that a is 0 and b is 1, and it follows that if S1 forms a group under E, okay, then the identity element has to be equal to 1, 0. Okay, then there is just no other option. Okay. So this was the rough work that we did, or one can do, or I did, in order to be able to just write this one sentence. Okay, to be able to write this one sentence, I needed to first figure out what would work. Okay, and now once that is done, again here you need to come up with x1, y1 and x2, y2. That one can also arrive at this conclusion that for this choice of x1, y1, x2, y2, we have the desired condition. Okay. So again, one can do some similar computation to see that x comma minus y is the right choice, or if there is any right choice at all, that has to be x comma minus y. Okay, great. Here is an example. So some of you have already come up with all that, because I asked you to be able to write down or at least to provide at least 5 distinct examples of groups. In case you have, some of you might have come up with all these examples. Okay, right? So the set of integers with respect to addition, that forms a group. Set of real numbers under addition, that also forms a group, and so on. So they are denoted by z comma plus, r comma plus, and then c comma plus, and so on. Okay. So now, you can ask what happens if we replace addition by multiplication. Okay, so do they form a group? That's an interesting question to ask. So here is that question for you. So which of these sets among Z and R and C, they form a group under multiplication? Okay, so here, of course, we have started with sets. So for instance, if we just focus on this set of real numbers, for instance, so there if you deal with real numbers, then they form a group under, just give me a moment. So we need to start with a set, and then you need to have a composition law. So the composition law is the multiplication. You pick 2 real numbers x and y and send it to x times y. Okay, so here the composition law is x star y is equal to xy. So here is the usual multiplication of real numbers. Okay, then you see that since the set of real numbers contain the product of any two reals, so this composition law is well defined. You also know that multiplication of real numbers is associative, right? So you also have the third condition here. Okay, that is something that you already know. So what is left out is to focus on the fourth and the fifth condition: existence of identity and existence of inverse, etc. Right? Okay, great. Anyway, so here are also certain examples that R cross and C cross, they denote set of all non-zero real and non-zero complex numbers. So then you can show that they form groups under multiplication. Okay, so here is one example, or rather one exercise. So why did I include that? So let me try to explain a bit, because in the previous lecture, when we were we came up with this, or rather we discussed this notion of groups, right? We came up before that we discussed several examples, and for instance, here in this remark, we first we were trying to speculate how to formalize the notion of symmetries. Okay, so here is a non-empty set consisting of certain symmetries of an object, and by symmetry, when you're trying to formalize or you're trying to come up with the notion of symmetry, we thought that we can define that to be a bijection f from x to x, right? And whenever you have got two bijections f and g, you can compose them. That will give us another bijection g composed f, and so on, right? Yeah. So here is an example that tells you that if you consider bijections of certain objects, or maybe at least certain bijections of some objects, then you end up getting a group. Okay. So for instance, if your object is R2, so here x is R2, so you can go back to remark 6 or around remark 6. Yeah, so you take x to be R2, so from R2 to R2 you define this map f alpha beta. So alpha beta is either 1 1 or 1 minus 1, etc., right? So you look at this map f alpha beta from R2 to R2, which sends x comma y to alpha x comma beta y. So you just put these two signs in front of these two coordinates, right? You can check that this is a bijection. Okay, anyway, that is not something that is, anyway, so I take that comment back. So you can check that this is a bijection, and the exercise is to determine whether this set consisting of all these bijections, where alpha beta vary over this set. So altogether you have got 4 such bijections here, f11, f1 minus 1, and so on. So these 4 bijections together, whether this set form a group or not under composition of functions. Okay. Yeah, so here you will get to see that for this object x equal to R2, certain bijections, a bunch of certain bijections together, they form a group under composition of functions. Okay. Anyway, so this is an interesting exercise. I think you should be able to do, because you have already seen one such thing. Yeah, here this one, the reflection map. It sends x comma y to x comma minus y. So you're just trying to come up with some, a variant of this map, right? Or maybe 4 variants of this map. So we just introduce the signs here, right? The signs alpha beta, right? Okay, great. So here is an exercise. So another exercise for you. Maybe I should call it exercise number 25. So your task is to generalize exercise 24. Okay, so you can try to generalize in whichever way you would like to. Okay, and yeah, so try to work on it. Try to go through exercise 24. Write down a solution. Okay, by solution I mean a detailed solution. Okay, so here is something that we often miss out, because a neatly written solution is far from doing any rough work. Okay, even you see this, this doesn't qualify to be a rough work, because this appears to be too neat. Okay, so when I do some rough work, that is something that I cannot understand after maybe a couple of days. Okay, because there are no sentences, just certain notations written and so on. Okay, so while solving these exercises, of course you need to do certain rough work, or maybe certain computations, or certain computations that only you can understand at that specific moment. But while writing solutions, please write down detailed solutions. This is important, for several reasons. This will help you to prepare before the quizzes, before the final sem exam, or maybe even at a later time you'd like to, maybe after 5 years from now on, you'd like to go back to, or maybe even after 2 years, you'd like to go back to the notion of groups that you have learned, and if you have your copy at that time along with you, then you can go back to that notebook in order to see the kind of thoughts that you had in mind. Okay, if you have just done certain sketches, or you have just scribbled your thoughts over your notebook, that won't make any sense to you after a couple of years, or maybe just even a couple of days. Yeah, anyway, so here you are dealing with bijections of this set R2. So more generally, you can start with a non-empty set X, and here is an exercise for you to show that the set of all bijections from X to X, that forms a group, okay, under composition of functions. Okay, yeah, so please try to work on these exercises, and that's all for today. All for today's lecture. And yeah, so please try to go through the lecture notes carefully If you have any questions, or comments, please feel free to discuss those questions with your tutors during the tutorial sessions, and also feel free to join the office hours in order to, have a chat with me. So please feel free, okay? But do continue to uh, read these lecture notes, work on the exercises, okay? And yeah, so with these two lectures, I think you are in a good position to uh, post a somewhat detailed problem set. Okay, I'll try to do that. So I was just waiting for this lecture because in the last lecture we just defined this notion of groups. I could have given certain exercises for you to work on. Sorry, but before that, I wanted to first solve, or I just like to tell you how to write down a solution of such an exercise, where you will be given a set and you will be given a composition law, and you needed to see whether that set forms a group under the given composition law or not. Okay, and also here is a task to, you can have faith on the question, but but to be sure of what you are doing, or just to be sure of the setup, it's important to verify whether that map star is well defined or not. In other words, if you want whether the image of the map star is contained inside this underlying set S1. Okay, so with that we stop this lecture, we conclude here.